high voltage current transformer, or CT, measures amperage on a shielded high voltage cable by using the principle of electromagnetic induction. Here is how it functions. Current flows through the primary conductor of the shielded cable. This current flow generates a magnetic field around the primary conductor. The shielded cable features a conductive shield that surrounds the primary conductor. The shield is generally grounded to prevent external electromagnetic interference. The CT contains a secondary winding, which is made of conductive wire wrapped around a core. The CT is placed on or around the shielded cable. The magnetic field produced by the primary conductor penetrates through the grounded shield and links with the secondary winding of the CT. According to Faraday's law of electromagnetic induction, the varying magnetic flux induces an electromotive force, or EMF, in the secondary winding. The induced EMF causes a current to flow in the secondary winding of the CT. This secondary current is proportional to the primary current flowing in the shielded cable. While the shield around the primary conductor reduces the inductance compared to an unshielded cable, it does not completely eliminate it. The magnetic flux created by the primary current still has some inductance that can be sensed by the CT. The CT measures the magnetic field generated by the current flowing in the shielded cable. The grounded shield prevents external magnetic interference but does not completely eliminate inductance. The CT can accurately measure amperage in a primary conductor even with a shielded cable. To further understand how a CT measures amperage, it is important to delve into the core principles and components involved. Firstly, the current transformer is designed to accurately reflect the current flowing through a conductor at a different, typically lower, level. This is crucial for safely monitoring high currents without directly connecting sensitive measuring equipment to the high voltage circuits. Secondly, the grounded shield plays a significant role in managing electromagnetic interference. By grounding the shield, external noise and unwanted signals are diverted away from the primary conductor, ensuring that the CT accurately measures the current flowing within the cable, rather than being influenced by external electromagnetic fields. Thirdly, the key is in the electromagnetic induction process. The current flowing through the primary conductor creates a magnetic field. This field then induces a current in the secondary winding of the CT. The relationship between the primary and secondary currents is determined by the turns ratio of the CT, which is a precise design parameter. Fourthly, it is important to note that the magnetic flux generated by the primary current must penetrate the grounded shield to reach the secondary winding. Although the shield is designed to minimize external interference, it cannot completely block the magnetic flux generated by the primary current. A portion of this flux still links with the secondary winding, enabling the CT to measure the current. Fifthly, the accuracy of the current measurement depends on several factors, including the quality of the CT, the design of the shielded cable, and the grounding of the shield. High-quality CT are designed to minimize errors and provide accurate readings, even in the presence of electromagnetic interference. Sixthly, Faraday's law is at the heart of this process. This law states that a changing magnetic field induces an electromotive force, EMF, in a conductor. In the context of the CT, the changing magnetic field generated by the primary current induces an EMF in the secondary winding, which then drives the secondary current. Seventhly, the inductance of the shielded cable is a factor to consider. While the shield reduces the overall inductance, it does not eliminate it entirely. The remaining inductance is sufficient for the CT to sense the magnetic field and measure the current. Eighthly, the turns ratio of the CT is a critical parameter. This ratio determines the relationship between the primary current and the secondary current. For example, a CT with a turns ratio of 100:5 means that for every 100 amps flowing in the primary conductor, 5 amps will flow in the secondary winding. Ninthly, the design of the CT core is crucial for its performance. The core is typically made of a ferromagnetic material, which helps to concentrate the magnetic flux and improve the efficiency of the induction process. Lastly, the grounding of the shielded cable is essential for safety and accuracy. Proper grounding ensures that the shield effectively diverts external interference and prevents voltage buildup on the shield. In summary, a high-voltage CT measures amperage on a shielded cable by utilizing the principles of electromagnetic induction and carefully managing electromagnetic interference through grounding and shielding. The CT design, including its turns ratio, core material, and secondary winding, is optimized to accurately reflect primary current at a safe and measurable level. The grounded shield plays a crucial role in ensuring that the CT measures the current flowing within the cable, rather than being influenced by external factors. Let's now explore the practical applications and implications of using CT with shielded cables. Firstly, consider power distribution systems. High-voltage cables are extensively used in power distribution networks to transmit electricity from generating stations to substations and then to end users. In these applications, it is crucial to monitor the current flowing through the cables to ensure that they are operating within their safe limits and to detect any overcurrent or fault conditions. Secondly, industrial facilities often employ shielded cables to power large machinery and equipment. CT are used to monitor the current flowing through these cables to optimize energy consumption and to prevent equipment failures. Thirdly, in renewable energy systems such as solar and wind farms, high-voltage cables are used to transmit the generated electricity to the grid. CT play a vital role in monitoring the current flow and ensuring the stability and reliability of the grid. Fourthly, CT are also used in protective relaying systems. These systems are designed to automatically disconnect a circuit in the event of a fault, such as a short circuit or an overload. CT provide the current information that is used by the protective relays to detect these faults and initiate the appropriate protective action. Fifthly, in research and development, CT are used to measure the current flowing through high-voltage cables in various experiments and tests. This information is used to evaluate the performance of the cables and to develop new and improved designs. Sixthly, the use of shielded cables is particularly important in environments where electromagnetic interference is a concern. For example, in hospitals and data centers, shielded cables are used to prevent interference with sensitive electronic equipment. CT are used to monitor the current flowing through these cables without introducing additional interference. Seventhly, the selection of the appropriate CT for a specific application depends on several factors, including the voltage and current levels, the frequency of the current, and the accuracy requirements. It is important to choose a CT that is designed for use with shielded cables and that meets the specific needs of the application. Eighthly, the installation of CT on shielded cables requires careful attention to detail. The CT must be properly aligned with the cable and securely mounted to ensure accurate measurements. The connections to the secondary winding must be made with the correct polarity to avoid errors. Ninthly, regular maintenance and testing of CT are essential to ensure their continued accuracy and reliability. This includes visual inspections, insulation resistance tests, and ratio tests. Lastly, the data collected by CT can be used for a variety of purposes, including energy monitoring, load management, and predictive maintenance. By analyzing the current flow patterns, it is possible to identify potential problems and take corrective action before they lead to equipment failures or power outages. In addition to the above, let's consider some advanced applications of CT with shielded cables. One advanced application involves harmonic current measurement. Harmonics are unwanted frequencies that can distort the current waveform and cause problems for electrical equipment. CT can be used to measure the harmonic content of the current flowing through shielded cables, allowing engineers to identify and mitigate harmonic distortion. Another advanced application involves power quality monitoring. Power quality refers to the characteristics of the electrical power supply such as voltage stability, frequency stability, and harmonic content. CT can be used to monitor various power quality parameters and provide valuable information for maintaining a healthy power system. Furthermore, CT are used in advanced metering infrastructure, or AMI systems. AMI systems are used to collect and analyze data from smart meters, providing utilities with valuable information about energy consumption patterns. CT play a role in accurately measuring the current flowing through the cables connected to the smart meters. Considering safety aspects, it is extremely important to follow proper safety procedures when working with high-voltage CT and shielded cables. Only qualified personnel should perform installation, maintenance, and testing tasks. Always de-energize the circuit before working on CT or cables. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow all applicable electrical codes and standards. Now let's address some frequently asked questions about CT and shielded cables. One common question is whether the shield affects the accuracy of the CT measurement. As explained earlier, the grounded shield does not completely eliminate the magnetic flux generated by the primary current. The CT is designed to accurately measure the current even with the presence of the shield. Another question is whether the type of shielding material affects the CT measurement. The shielding material can have a slight effect on the magnetic flux distribution, but this effect is generally negligible for most applications. The CT calibration can compensate for any minor variations due to the shielding material. Another question is whether the length of the shielded cable affects the CT measurement. The length of the cable has a minimal effect on the CT measurement as long as the CT is properly installed and calibrated. It's essential to ensure that the CT is positioned correctly relative to the cable and that the connections are secure. Let's now consider the environmental factors that can affect CT performance. Temperature variations can affect the accuracy of CT. It's important to select CT that are designed for the specific temperature range of the application. Humidity can also affect CT performance, especially in outdoor environments. Choose CT that are properly sealed and protected from moisture. Lastly, vibration and shock can affect the accuracy and reliability of CT. Ensure that the CT are securely mounted and protected from excessive vibration or shock. In conclusion, high-voltage CT are essential components for measuring amperage on shielded cables. They rely on the principle of electromagnetic induction to accurately reflect the current flowing through the primary conductor. The grounded shield plays a critical role in minimizing electromagnetic interference, while the CT design ensures accurate measurements even in the presence of the shield. Understanding the principles of CT operation, the role of the shield, and the various factors that can affect CT performance is crucial for ensuring the safe and reliable operation of electrical systems. The applications of CT with shielded cables are vast, ranging from power distribution systems to industrial facilities and renewable energy systems. By properly selecting, installing, and maintaining CT, engineers and technicians can accurately monitor current flow, optimize energy consumption, prevent equipment failures, and ensure the stability and reliability of electrical power grids.